Video 61 of the master course Quantum Chemistry of Molecular Electromagnetic Properties. The topic of this lecture is Hartree-Fock theory. Closed-shell Hartree-Fock theory, sometimes also called self-consistent field theory, is the theory where the unperturbed electron wave function is approximated by one single Slater determinant. The spatial orbitals necessary for the spin orbitals, which make up this Slater determinant, they are obtained from an eigenvalue equation, which are called the Hartree-Fock equations, where here we have the spatial orbital, here we have the Fock operator, which is an effective one electron operator, and here we have the eigenvalue, which is called the orbital energies. The Hartree-Fock energy is calculated as the expectation value of this single Slater determinant, called the Hartree-Fock or self-consistent field determinant, and the full electronic unperturbed Hamilton operator. The Hartree-Fock equations are derived from this expression for the energy using the variational principle. So they are derived from the condition that the Hartree-Fock energy is stationary with respect to a variation, an infinitely small variation in all the different spin orbitals, psi p. So the linear variation of the SDF energy or Hartree-Fock energy is equal to 0. In addition to this, there's the constraint that the spin orbitals remain orthonormal. Starting from these two conditions, or this condition and this constraint, one then can derive the Hartree-Fock equations for the spin orbitals and then integrate over spin in order to get the Hartree-Fock equations for the spatial orbitals. We want now to define a new operator, which I want to call the Hartree-Fock Hamiltonian, which clearly has to be distinguished from the electronic Hamiltonian, H. And this Hartree-Fock Hamiltonian is just the sum of all the Fock operators for all the electrons. Where here we have implicit defined also what the Fock operator is. It's the so-called core Hamiltonian. That's one electron operator, which consists of the kinetic energy operator for electron I, and the operator for the Coulomb interaction between electron I and all the nuclei in the molecule which we consider. In addition to this so-called core Hamiltonian, there is the effective one electron potential called the Hartree-Fock potential, which describes the averaged interaction of electron I with all the other electrons in the system. Looking at this effective operator, we can see here the interaction between electron I and a second electron. So this is the Coulomb operator for the interaction between electron I and the second electron. And here with phi j complex conjugate times phi j, we have the probability for finding electron 2 at the position R2. And together with the elementary charge here, this is just the charge distribution or the charge density of electron 2. And you can see we integrate over the positions of electron 2, and therefore we don't have the instantaneous interaction between electron I and a second electron, but we have the averaged interaction between electron I and an electron which is in the orbital phi j, in the occupied orbital phi j. And then we sum over all the occupied orbitals j, so we get the interaction between electron I and all the other electrons. Actually, because we sum over j here, we actually also include the self-interaction, but the self-interaction disappears again because this is actually two integrals. We have the normal integral and we have an integral where in the right-hand side, sort of in the ket of the two electron integral, electron 1 and 2 is interchanged. But if electron 1 and 2 are the same, then this cancels the first one. So the self-interaction is actually cancelled. Now in order to calculate this integral here, which means to calculate the charge distribution of the other electron, we of course need to have this orbital phi j, and they are of course also solution to the Hartree-Fock equations, which means that the Fock operator, where this Hartree-Fock potential is a part of it, actually depends on its own eigenfunction, which means one has to solve the Hartree-Fock equations iteratively until self-consistently, meaning until the orbitals which we get as solution to the Hartree-Fock equation do not differ significantly anymore from the orbitals which we use to calculate this Hartree-Fock potential. And that's the reason that one has to solve these equations to self-consistency is why one also calls this the self-consistent field method. Now the eigenvalues then, when one has reached self-consistently, the eigenvalues, which are then the diagonal elements of the Fock operator, they look like this, where here we have the kinetic energy and the electron nuclear interaction contribution, and here the contribution from the averaged interaction between the electron we look at and all the other electrons. Here it's written in terms of spin orbitals, psi, and here we can write it in terms of spatial orbitals. The factor 2 here appears because here in the sum over occupied spin orbitals, we of course have twice as many occupied spin orbitals as we have occupied spatial orbitals, because we have the alpha and beta spin orbitals. So that's why we have 2 here. The 2 is missing from this term, because there we would have that the second electron would have a different spin than the first electron, electron 1 here, and so the second integral would be cancelled due to the spin integration. The spin orbitals with the lowest energy, and precisely the n spin orbitals with the lowest energy, or the n divided by 2 spatial orbitals with the lowest energy, are then used to construct the n-electron Slater determinant. And they are therefore called the occupied orbitals, and in the following they will be denoted by the Latin indices I, J, K, and so forth. The other solutions to the Hartree-Fock equations, meaning spin or spatial orbitals with higher energy than the lowest n spin orbitals, or n divided by 2 spatial orbitals, they are not used in the Hartree-Fock Slater determinant for the ground state, and they are therefore called the unoccupied or virtual orbitals, and they are indicated by indices A, B, C, D, and so forth. And if you don't want to distinguish between occupied or virtual orbitals, just talk about a generic orbital, then we use the indices P, Q, R, and so forth. Now, the Hartree-Fock wave function, meaning this single Slater determinant made from the spin orbitals with the lowest energy, the n spin orbitals with the lowest energy, this Hartree-Fock wave function actually turns out to be an eigenfunction of this Hartree-Fock Hamiltonian. That's not very difficult to see, because the Hartree-Fock determinant is an antisymmetrized product of the spin orbitals, whereas this Hartree-Fock Hamiltonian is just the sum of the different Fock operators. And if we then remember that each spin orbital, of course, is an eigenfunction of one of these operators, one of these one-electron Fock operators, then it should be easy to understand that the product of spin orbitals is going to be an eigenfunction of the sum of the Fock operators. And so it is. The eigenvalues are then the sum of the orbital energies, which means the eigenvalue is not the Hartree-Fock energy, but it's just the sum of the orbital energies. So one might ask why to calculate the Hartree-Fock energy as it is, as the expectational value of the full Hamilton operator, instead of just using the sum of orbital energies. There's a good reason for that, because we should remember that the orbital energies include the kinetic energy of that electron, the interaction with the nuclei, and then the interaction with all the other electrons. That means if we sum the orbital energies, then we have summed the interaction between the electrons twice. And that's of course not what we want. So let's look at the expression for the Hartree-Fock energy. As I said, it's the expectation value of the Fuhrmann-Hamilton operator. And there we get now here the sum of all the kinetic energy and electron nuclear attraction contributions, because we sum here over all occupied orbitals. And then we have a double sum over all the occupied orbitals, but we have in front of it 1 over 2 over the integrals here, which represent the averaged electron-electron interaction. Instead of this double sum where I and j run freely and dividing by 2 in order, which removes the double counting, one might as well write restrict the second sum j so that it only j only can take values which are smaller than I. Now we can rewrite the Hartree-Fock energy making use of the expression for the orbital energy, which is done here. We have a sum over all the orbital energies, but as I said, if one sums over all the orbital energies, then one double counts the electron-electron interaction, the average electron-electron interaction. So if one inserts the expression, one can see that in the Hartree-Fock energy, this averaged electron-electron interaction, this double counting, is removed because we subtract here 1/2 of it again. In the next slide, these expressions are all in spin orbitals. So in the next slide, I have the corresponding expression for the Hartree-Fock energy in terms of spatial orbitals. And because the spatial orbitals are doubly occupied, so I have a 2 here and also a 2 again here. Except for the so-called exchange integral, the 2 is missing again because of the spin integration. And finally, I also have the corresponding expression where I make use of the orbital energies. Here the sum over the orbital energies for the occupied spatial orbitals times 2, because there are 2 electrons in each of them. And then here the averaged electron-electron interaction, where the first integral is sort of the Coulomb integral and the second one is the exchange contribution. Now, the Hartree-Fock equations, we looked at them right now in the terms of an eigenvalue equation, but in reality they are differential equations, so meaning the orbitals are a solution to these differential equations. And one way to solve this equation is by expanding the unknown spatial orbitals in the basis set, as we discussed already in the last lecture. If one does that, one in the Hartree-Fock equations, one comes to what is called the Rutherford-Hartree-Fock approach, where, as I said, molecular orbitals are expanded in these atomic orbitals or basis functions. That turns the Hartree-Fock equations actually into matrix equations, and the solution to these matrix equations are then the molecular orbital coefficients. And the variational condition for solving which can be used to derive the Rutherford-Hartree-Fock equations, is then that the Hartree-Fock energy is a stationary point with respect to variations in the molecular orbital coefficients. So I can derive them by saying that the derivative of the Hartree-Fock energy with respect to all the molecular orbital coefficients has to be 0. And remembering that the Hartree-Fock energy is the expectation value of the full Hamiltonian with our Hartree-Fock wave function, this must imply, and the Hamiltonian of course does not depend on the molecular orbital coefficient, this must imply that this condition must be fulfilled, where I have that the integral here, where I have the Hartree-Fock wave function in either the bra and the ket, and then the derivative of the Hartree-Fock wave function in the corresponding ket or bra then, with respect to the molecular orbital coefficient, and this has to be 0. Later on, we actually will make use of these expressions here and use that they are 0 in some derivations where we assume that we have the optimized Hartree-Fock wave function.